Good morning, everyone. My name is Agustin. I work in the support team at Percona. I am from Uruguay, and I know I should be doing this in Portuguese, but I promise I would never do it again. So this is the best for everyone here. And we're going to be discussing optimizing your PostgreSQL instances, or the top. Actually, this is going to be about the top configuration variables you will want to check when you newly deploy your instances, or if you have your environment currently set up already and you want to see if you can have any easy gains. You will need to go through this list of configuration variables and then check if they are correctly set. This, I would say, is like an 80-20 rule. So with the least amount of effort, you would get the most benefits. And I think that this list is, if you ask any Postgres database engineer, I would expect the top 10 to be fairly similar, or at least contain the top 5 that we're going to mention in some moment. So the motivation here is, with the least amount of effort, do the most of the work, right? And the brief agenda is, we're going to see these incident statistics that they are based on our experience with customer environments at Percona. And then we're going to review some candidate configuration variables that we should check what they do and how we can size them correctly for our instances. And then very important point here, and I would like to stress that this is super needed if you want to do any kind of optimization work. You should have monitoring and observability in your environments, because otherwise, this is Brendan Gregg has many anti-patterns. One of it is like the drunken optimization. Is like you go in there, randomly change a variable to a random number and expect the best to happen, and you will, of course, easily know that this is not going to work. So monitoring and observability is a big, at least in my experience, is a big area that we should be working on. So the motivation behind this is, we were saying 80-20, right? So if you go to the latest Postgres 16, the latest stable version, it's going to have 366 variables without including any extensions, right? So this is the bare minimum that you will have. From here, you would only increase the amount of configuration variables that you would need to tune. So you have either the possibility of going through this list extensively, checking all the descriptions and see if you could improve it, or you could have a magical list that will help you choose the ones that you need to check first, improve, configure, optimize, do a loop on observability changes, and see how they how the environments behave to these changes. And then you could go through the other 356 for you to check and see if you can do any, let's say, micro optimizations. As you are probably familiar already, there is like a theorem of diminishing returns. So maybe it's easy for you to double, triple, or 10x the performance, but after that you will have to put in much more work that you initially did to have those 2 times more, 3 times more. You would have to actually put in a lot of more work to be able to optimize it that much again. So I would say that these whatever top N configurations that you will check are the 80-20 that I was saying before, because you can do 80% of the performance, and then that 20% you will want to check if you want to do it at a later stage or not. But that will be more work for you, because not only you will have to be familiar with all the configurations, you have to know what they do and how they interact with each other, which sometimes it's a bit tricky in of itself. So yeah, the motivation here is just to do the best with our time and with our available resources in the easiest way. So is there a foolproof list of variables that we can tune to magically improve our performance? Of course, the answer to this is no. It will depend on what our workload is. It could be write intensive, read intensive, OLTP, OLAP, whatever. There is a plethora of environments around, and there is not a silver bullet that I will tell set shared buffers to a magical number and it will work. So it's important to know what these variables do, how they interact with each other, and what values we can give to them so that we can expect the best behavior. So how can we assess which candidates to pick first? This is what this list is all about. So if you trust in what I'm going to say, you would then take this list, get these candidates, optimize them, and then hopefully you will get enough performance improvements so that you can forget and move on to your next environment. And then again, the point I want to stress here is how we can measure and quantify the improvements or not. Maybe we tune a variable and we notice that there is a regression in performance that happens all the time. So we need to be aware of how the system is responding to these changes. Okay, so now I'm going to discuss this list. This is, we worked on this with a colleague from the support team, Pablo Svampa. He's from Argentina. And we have actually delivered this talk before, and we have been iteratively and incrementally improving this. So if you see any variable that you have worked on in the past not here, and you would like to discuss it, I would be more than happy. We've had inputs in the past, not with the top 5, that's for sure. That we will all agree that that's what should be. But maybe there is a variable that you have worked on and you won't see here, and I would be more than glad to discuss it with you guys and turn the presentation accordingly, right? So again, this is from our experience at Percona with our customers, with their environments. I would like to say that this is not homogeneous, right? So we can have customers from any kind of walks of life, let's say, right? So from small servers to big servers, 1 mega database, a trillion small databases, using Kubernetes, using whatever you can imagine, right? So I think this is a good representation of the database world in of itself, right? So I may be wrong, but I think this is fairly accurate. And if you asked me before gathering this data and before doing this research, I would say that these top 5 would be the same. Maybe not in the same order, and we're going to check why. But definitely this is the top 5 configuration variables that you want to check. So if you want to take a screenshot here and go now, that's that you will get 80% of the talk, and you can do this research afterwards. But if you're going to take a picture, do it now from this screen, because these are the variables that you should be checking, right? And I would say not even the top 10, because you may not get any huge performance gains from setting wall level. It's unless you disable it. So unless you lower it. So or mean wall size, it's also not going to give you a huge performance boost. But top five, I would say you should always not tune, but want to check. You will always want to check, and you will always want to see if for your environment in particular the defaults apply. So Postgres, as with other database systems, Postgres' intention is for defaults to work fairly well in most of deployments available, most of environments available, right? So these defaults will work on your Raspberry Pi and on your mega server with 500 cores and 3 terabytes of RAM, right? The issue here is obvious. The mega server will be underutilized, right? So this is the give and take on defaults, on choosing defaults. You want them to run anywhere? Yes, perfect. It will run even in a credit card, but it will not be optimal or performed for all of the devices, right? So with any workload that is not a toy workload, you will want to tune these top 5 configuration variables. I have a full list of top 25, and the incidence percentage that you can see here is how we decided to sort these, and this is our sorting function, let's say. So the more this max connections string appeared in 12% of our tickets, be it that it was optimized or the culprit behind the optimization, the performance issues, right? So I'm not only saying that max connections can improve your performance, it can also plummet down to a halt, right? So if you have, we are going to discuss it briefly now, but if you have way more max connections that your server can handle it, it could become useless, start thrashing, and it will start do more context switching than actual work, right? So it's not always about performance, but stability also, right? So again, top 5, this is what you want to check. We have top 25. You can use this as an aid in lowering that 366 number that we saw before. You don't have to read all of them. Just go through the top 25 here, and that's a good beginning if you want to make yourself more familiar with the whole of configuration variables available on Postgres. So this is a great start. And it's kind of as a validation of our research, and as I was saying, we have been doing this talk for a while now. This is a table that we got 2 years ago, and this is a table I got for this talk. So as you can see, the top 5 has remained the same. We have a slight change into in the places that work mem and shared buffers have. It's really minimal, but again, the top 5 has remained unchanged, and this is what I would expect even for years to come in terms of optimization for PostgreSQL, right? So I'm not saying this is perfect, but this has been working fairly well in these years. So let's start reviewing. Sorry, at what time did we start? 35, something like that? Perfect, thank you. So let's review the top candidate configurations, and the QR code that is going to be at the end is going to have the slides. We've extensively added all of the top 25 definitions and mentions here, and the ones that we are interested in are going to be in green, right? Those are the top 5. So we have added the sections as you have in the Postgres online documentation manual, so that you have a reference. So the subtitles here are going to be the Postgres documentation subsections, and then it's going to include the variables, right? So this is going to be about connections and authentication and client connection defaults, and the next one is going to have resource usage, right? So you can easily go and find these in the documentation manual. So max connections was, if you remember, our top 1 variable. So it appeared in 20% of our tickets as either an improvement or the culprit behind the issues. As you probably already know, Postgres is going to spawn a fully fledged OS process for every connection that you start. It's not unlike some other database systems that may use lightweight processes or threads. Postgres uses the full, it does fork, right? So it uses a full process to handle a connection, right? This can have a severe toll on how the server reacts to a spike in load. So we've seen many customers say, okay, application, how many connections do you need? Oh yeah, okay, we will have, I don't know, 1,000 users. We want to be able to absorb any spikes or any issues. Please give us a maximum allowed number of connections of 2,500. And then the database engineer says, okay, yeah, max connections, 2,500. and the server is, I don't know, 32 CPUs, whatever RAM and I/O you want, right? So what happens? Everything is working normally. You have 100, 200 users connected. Everything is working fine. Now you do release a new functionality. You have a new user base connection incoming, and you now have 500, 600, 1,000 connections. And then that server stops working altogether. It will refuse to work because there is something that is called thrashing at one point. And this you can see as graphed as an increase. The server can, if the server can handle the load, you would get an increase in connections, an increase in server load. But there comes a time where you reach the top of the mountain, let's say, and the server starts doing more work to handle the connections and the context switching between the connections than actual work itself. So work starts to pile up, and you get queuing. And at one point, the server is just simply not doing any work at all and just switching between active connections or active processes, if you want, and then switching to another one before being able to do any work. The time slice has depleted for that process. It changes to another, but it has not done any work. That is called thrashing, and that is a really bad state for your server to be in. And Max Connections can do this, again, because Postgres is using fully fledged processes. So we would suggest, and this is what we suggest to our customers, if I would have to blindly choose a setting for this, I would go 10 times your virtual CPUs, right? So if you have 32 cores, I would set this to 320. If your application needs more, that is not the end of the world, and that is why we have connection poolers, Postgres. So if your application needs more than that, you can either scale up your hardware resources, and then you wouldn't need the connection pooler, or you should start thinking of introducing middleware there as connection pooler, right? Of course, this is not a magic number. Maybe in your case, 20 times CPUs, the amount of CPUs work, but it's going to be around that, right? So if your application will always need to use this amount of connections, then the two choices you have is hardware or a connection pooler, right? From these other ones, I would say that this gets an honorific mention because it has been used in the past to when the application and database teams are not coordinated enough, or there is a devs, there is a discrepancy how they see things. They not always use the database resources as we should, right? So they start the transaction, they do something, and then they go back to do whatever they want for 10 minutes and then come back and the transaction is still ongoing. That is holding on resources, logs, etc. And that has been the issue with some of our customers before. And how you would see it, if you have a lot of connections in the states idling transaction, then this is an issue coming from the application. They need to, typically, I would say it could be otherwise, but they should be handling that connection more effectively. If they are if they are not compliant with how connections should work, and you need to be more strict, you can use this session timeout for idling transaction state, so that it gets. You don't have to use 2 seconds. You can say, okay, I will give you 1 minute, and that's more than enough. And bear in mind, this is only if the application doesn't do anything for 1 minute, right? So if you do a select, wait 2 seconds and do another select, that's totally fine. That's not idling transaction. If it's running a query, it is active. So again, you can do 1 minute or whatever. But this has always also solved issues, especially if you are on the run and you have to recover a server from having severe issues related to connections. Okay, let's go through quickly through resource usage. This is except the usage coming from write-ahead log, right? So workmem is used for helping queries have more resources to run, so they will run more optimally. But this is a case in which I would say if you need to tune this, I would suggest that you really have a discussion with the application team and you do this only per session. So you don't want to increase this globally because this can be used many times for one query, depending on the operations that need to be done. So if you do, let's say, if you do an order by these things, you could use 2 times the workman. And if you increase this to 128, let's say, because you think that is optimal, and you have 100 connections doing this query, you can imagine how that explodes, right? So this is one configuration that I would say definitely needs coordination between the application team and the database team, right? So this is not something you would like to tune on the database server itself, but you would like to say to the application for this query, and this query, or for this transaction, before when you open the connection, you will, or when before starting the transaction, you will want to set this for your session alone, okay? But this can be the source of great improvements in your query performance, right? Sometimes giving a bit more to some queries can already rid you from issues with global logs or other resource logs usages that these queries can be behind. And then this is like our, I think it was top 3, or I think it was top 3. I would say this is top 1, and this is the discrepancy. Max connections, yeah, it can give you troubles, but 100 is fine by default. You can change that or not. But shared buffers, I would say, don't start your servers before checking this, because this is the PostgreSQL cache that PostgreSQL is in charge of, right? So how does PostgreSQL, in a nutshell, how does PostgreSQL memory access work? It has a cache of its own, and then it will use the Linux page cache, right? So Postgres doesn't do direct access to disk, so it will go through the OS cache, right? The OS cache is living in your RAM. So as by default, and this was one of the settings I was saying, that by default this will work anywhere, but then it won't be optimal for your, most likely won't be optimal for your workload in particular, unless you have really small workloads. This, I would say, to begin with, you can start with setting it to 25% of your available RAM, and then the other 75% is going to be shared with the page cache. The other processes like connections or other like a backup if you run it in the server itself, etc., and the OS, right? So if you need more, and we are going to check at the end how you can gauge if you need more or not, how is Postgres accessing data from disk or from the page cache. If you need more, it is suggested for you to go up to 40%. Then after that, you may get diminishing returns on increasing that even further, because as we were saying, Postgres needs the OS page cache to work, right? To be honest, this is something I wanted to try for some time now, and I haven't had time. Is okay, what happens if we do it past 40? If we use 75, are we going to be okay yet? What are the issues with that? What happens if we need to do flash 50% of the cache, and then we don't have the OS enough OS cache to do that? So I'm not sure what the repercussions are of increasing much further than, let's say, 50%. So for now, I wouldn't suggest doing that. But yeah, you can try for yourself in your workload in particular and see how it behaves. Maybe you have an increase in performance. But safe, 25 to 40%, that range, you can do whatever you want, and it's going to be okay. If anyone has any questions, you can raise your hand. I can understand Portuguese, even if I can't speak any of it. Okay, say.
Or shared book. How do you see thinking of it? Yes, it's comparable to
It's compared to what?
when
Yes, it is. It's exactly that.
so how much memory you saw on the feed database?
Well, that we're going to check. I have a graph here that can show how you can know if that's being used. But in a big database, we've seen the need to increase it further than this initial 25, just because, and it depends on the workload, right? It depends if it's purely reads, I would say, or mostly reads, I would say do 40%. Don't think about it, because that is like it's not going to change much. The pages that you need are not going to change much. And then the interaction between the shared buffers and the page cache is going to be kind of optimal, because the page cache is going to have pages pre-warmed for you from disk. And then we are going to see how you could see if Postgres is telling you if it's reading, because Postgres asks the OS to do the I/O for it. The OS may do it from the page cache if the page is already loaded in memory, but you will never know it from Postgres side. You will also need to have OS metrics to see where this read is coming from, really. But again, I think the issue that increasing it further from 50% comes from writes mainly, I would say. But I haven't tested this. This is like from what how I understand it works. This is a potential problem you have, because if you need to write a lot, you will want to wait for the sync, right? And then that becomes a real write, and that becomes a real slow operation. But if you have 60% full and then you want to do a read, it may be async and you don't care, right? So in big setups, again, I would conform to this 25-40%, even if you have a lot of RAM, unless you can know exactly how the page cache is working and your I/O patterns. Unless you know that, I wouldn't try to tune that further. Yeah. Okay, and then we have these other configurations that I'm not going to delve into right now, but you have there for your own reading afterwards if you want. Now let's go to a wall. This is another very important section, and I've seen these as a pain point behind write heavy workloads, and almost no one tunes this, and it's like very easy to get 2, 3, or more times increasing performance. So the write ahead log, as you know, when we write to a database, we want to avoid doing random I/O, right? Because that's more expensive than doing sequential I/O, right? So for that, we have, like, let's say a man in the middle that is called the write ahead log. You may also know it by other definitions, but in Postgres it's wall log. And what this gives us is the ability to write random I/O sequentially, right? Which is much more performance even on fast SSDs. So this is something that, if you have the rotational disks, is much more visible. But even on SSDs, you can do a benchmark, and the sequential I/O is going to be faster than the random I/O. So we always want to have this, right? So these two are very important, and I would say the most important one of them is max wall size. If you have to do one, just do max wall size. How do they interact with each other? So what Postgres does is checkpoint timeout by default is 5 minutes. So Postgres will allow you to write records to the wall for 5 minutes, and then it will do a hard stop, and then that it will flash all that activity to disk, and it will create a checkpoint mark, so that if you have the PostgreSQL process crashing, it knows that up to that point, all of this random I/O has been synced to disk to the table pages themselves. So that is the database is consistent up to that point, right? So this has to do not only with sequential and random writes performance, it also has to do with the durability of the database. It is crash safe. You can kill -9 your Postgres instance, and it will come up. It will do the recovery process. It will reapply the walls, and it will magically work. This is behind all of this, right? So checkpoints are very important for you to be able to recover fast from a crash. So checkpoint timeout by default is 5 minutes, and this will depend on your business needs, right? So checkpoint timeout is, you can see it basically as a measure of the amount of work that Postgres potentially has to do in the event of a crash. Okay, bear in mind that the recovery process is single-threaded, so it could take more than this 5 minutes, because in Postgres you have parallel writes, right? So processes can write in parallel to this file, but when you have to do the actual recovery process, it will do it single-threaded. So that is, of course, not even linear growth, right? It could take more than 15 minutes to do a recovery, even if the checkpoint time was 5 minutes. So this is something, again, for you to test, and that will depend on your business needs, how fast you want to recover from a crash. Let's say you're fine with doing whatever time, and you have other means of recovering after a crash, be it replication or whatever other solution you can come up with. And let's now think in terms of avoiding I/O peaks, right? So checkpoint timeout will also help you lower the amount of I/O you are using. How? Because the checkpoint timeout is also governed by checkpoint completion target, which we have it here because we've seen it in the past, because the defaults were not as correctly set as they are now. Now it's 90%, and what this tells us is that Postgres will flash this activity that was coming from the walls. It will take 90% of the checkpoint timeout to do that flash. So it will say, let's say, throttle itself so that it doesn't do a huge peak of I/O trying to flash everything at once as fast as it can, right? So it will say, okay, I have this much I/O available. I'm being able to flash at 3 megabytes per second. I need to flash 30 gigabytes in 4 minutes. And then it throttles itself so that it does, 10 megabytes per second. And you will see the actual I/O usage being stable for the checkpointer activity, right? And this is very cool because you have a lot of control over your I/O and how Postgres is doing this synchronous, random I/O, right? But if, let's say, you increase your checkpoint, you don't care about recovery, as we mentioned before, and we suggest our customers that unless you have strict needs on your recovery process, you set this to 15 or 30 minutes or even more if you want. So that means that for 15 minutes, Postgres will not do anything, and then it will do a checkpoint that it will take 14 minutes to do the workload that it just had. But it doesn't stop there, because if max wall size is 1 gig by default, if in that checkpoint timeout you had more than 1 gig writes to the walls, that will be a checkpoint also, and that is known as a forced checkpoint. Okay? Because you have done more writes than the max wall size allowed. Okay? So even if you are using checkpoint timeout by default and you don't want to touch it, max wall size, you need to check it. You need to check it because if you are having a write-heavy application, this is probably not going to be enough. And it's super safe to increase this. You just need the disk space to account for it, right? So we've had customers using 50 gigs, 100 gigs, and even more. And that's fine. Because what we don't want is a peak of I/O, but we have terabytes of disks available, and we don't care about 100 gigs used on redo logs, on wall logs, right? So at the end, I'm going to show a graph that helps us tune this perfectly without even trying. And this is super cool, and I really like it, and I haven't seen it anywhere else. But of course, you can get queries and you can get data to do this same thing for you, okay? Now, mean wall size, it's here, but we just typically say, okay, do it, set it to 50% of your max wall size, and this will just try to reuse the files that you have already there. So it's not a super mega performance optimization, but it does less work, and less work is always welcome in our databases. As I said, checkpoint completion target, you can check it, but by default it's 90% now, 0.9, and it's perfectly fine that way, okay? Replication, we are not going to touch replication here, but if you have replication, you will want, before version 12, it's going to be wall keep segments, and from 30, so 12 and before, and 13 and above, wall keep size, right? This can mean that if your replication is lagging behind, you can make sure that it has the walls to recover. There are other methods so that we don't have to tune this variable, yes, but this is the easy way to deal with it, okay? And then finally, query tuning. Again, this is not the top 5, but it deserves an honorific mention. Random page cost can help the optimizer be more smart, because by default Postgres will favor doing full table scans because it's very cheap to do it in Postgres and very performant. But this also means that you may not be using an index for some queries in which you may want. Again, this random page cost is still having like a legacy value, assuming you are on rotational disks or hard disk drives. Now the random page cost, as I mentioned, even in SSDs there is a penalty of doing random I/O, but it's not as much of a penalty as it was before. So I think by default this is 4, and this is like a 4-to-1 ratio of random I/O versus otherwise. You can tune this to 1.1, so it's a bit more expensive, but not that much, so that it wouldn't absolutely in no case use an index, right? Effective cache size, you can read that afterwards. And then auto vacuum. Auto vacuum is known as being the problem child of Postgres, right? But there is really not much to say, at least in terms of performance optimization regards. So I have included these values here for you to check. If I have to briefly mention something, it would be if you would want to tune the vacuum cost limit. This is the if we try to do a fast definition, this is the I/O available for the auto vacuum process. So the auto vacuum process also throttles itself, and it will run and it will do, let's say, 200 operations, and then it will sleep itself until it wakes and does 200 operations again. So typically this is set a bit low, and if you are having a lot of updates and deletes, as you already know, this can be a problem in Postgres, and it could generate bloat and a whole heap of other issues. So if you're having write workloads that does updates, many updates and deletes, you will want to increase the vacuum cost limit so you can pump the auto vacuum a bit more. And if you need even more, more optimization from this, you can tune how fast the auto vacuum kicks in for each table. With these two variables, which are scale factor and threshold, right? Basically what they do is the threshold sets the minimum number of tuple changes for the auto vacuum to kick in, right? So let's say you have a table with 100 tuples, and this is set to 50. If you have 50 changes in tuples, either let's say updates or deletes, that will make it so that the auto vacuum is eligible to kick in. Now, the plot thickens a bit because also the scale factor kicks in. So this is the math is really easy, but these are two terms in one equation that they will need to be they will need to suffice at the same time, right? So the scale factor is the percentage of the tuples that need to change, and this is an addition, right? So let's say we have 0.1 as the scale factor, and we have the same 100 tuples, right? So 0.1 is 10%. So we need to have 10 tuples changed plus 50. So we need to have 60 tuples changed in that table so that the auto vacuum is eligible for running it on that table in particular. We could discuss this a whole lot more, how you can tune this correctly for your tables, how you can set cron jobs if you have problematic tables that don't apply into these general terms. But we don't have time now, so we won't. If you want to discuss this, let me know and we can do it. And then finally, these are not performance related. This will not give you any benefits. If anything, they will give you drawbacks in your performance because this has to write to the logs. But this comes hand in hand with the observability that we were mentioning before. And sometimes you want to pay the penalty because that will give you the tools you need to get a performance increase that vastly improves on that drawback itself, right? So these are some of the logging variables that we used in the past. Especially, I would like to mention, if you don't have any other monitoring, do use the log checkpoints and connections, disconnections, and the auto vacuum one, right? This one will log all queries, so it could all queries that take less than a threshold. So if, let's say, if you set it to 0, it will log everything. So this could really be hard on your I/O. I would say do it for some minutes, seconds, and then turn it off if you really want to dig deeper what's going on. But don't typically use this to 0 because it will absolutely trash your performance. Now, this is the last section. I think we're fairly fine. Perfect. Thank you. And this is something I really like in Procona. We really pride ourselves into being able to get all of this data from servers, either like we were discussing with the guys yesterday. In yesteryear, we've been doing this with text-based tools. So you have a bunch of numbers, and then you have to make sense of them. Nowadays, of course, we are using something better, which is using Grafana, a graphical user interface with nice graphs, and that you don't really have to dig deep and know everything about the database so that you can use them. And I think this is the most, the least amount of effort, and it will give you the most benefits. And of course, it's our tool, so I'm a bit biased, but whatever tool you want to use that graphs this kind of information will be useful. You don't have to use Procona monitoring and management, even if it's open source and free. It runs on premises, so we will never see your data, and you will have absolutely full control on your data. You can run it in a very small server to try it, and it doesn't really need much resources. So I really suggest you to try it out. But again, you can use whatever you want that has this information. So again, why do we want to have this? Why should we spend whatever amount of time we need into getting this information from our environment? Because otherwise, we won't know what we are doing. It's like, yeah, okay, well, we increased share buffers from 1 gig to 10. What does that mean? Is it, how are you measuring it? Is the application reporting back any metrics on the amount of time that the database is taking to respond back? Do you have internal measure on how much CPU, RAM, whatever you were using, the amount of time you spent actually searching for the data waiting for disk access, etc. So do you know anything about how that impacted in the end, your application? Because that's what we live for, right? We live for the application. So this is very important, and this is something that I see being neglected a lot. So hopefully this will help you change that if you are not currently doing it. And then this is something that is also very important. We have the top 5. Okay, I would suggest you to start by doing the shared buffers, and then not only because you will get a boost in your dopamine when you configure a variable and you see the performance increase, but because you will have more traceability on which variable is impacting your database in which way, right? So shared buffers needs a restart, but then setting max wall size doesn't need a database restart. So that is cheap to change, okay? So again, shared buffers, tune it, and then you can play with max wall size and see how things are working. And then my final piece of advice, if you will, or something that I see being done wrong in many cases, especially with AWS and how it collects data, is try to use as a low resolution as you can. By default in PMM, we are using 5-second resolution, and this is the cadence in which you gather data. It can go up to 1 second, so you can gather data every second if you want. Try to do it as low as you can. As low as this will, of course, have a toll in the database, because it's different if we are checking every 1 second, every 5 seconds, or every 1 minute. That's also a workload that the database has to reply back. But then bear in mind that you may be losing data to averages. So if you're collecting every whatever seconds, but then you're averaging over a minute, in a computer, as you already know, the clocks run at insanely high speeds. So 1 second is an eternity, right? So you can have changes in workloads that are in seconds or even sub-seconds, right? So if you aggregate that data in 1 minute, you will lose data in a sense, because it can mask peaks, right? So let's say you have 10 connections in 1 minute, but then in 1 second, the application uses 1,500 and then it stops using it. Yeah, the average will increase, but you won't see that peak. That is going to be masked in the average for 1 minute. So if possible, try to do it as slow as you can. It's not always possible, like AWS does it for you 1 minute, and that's the amount of data you have, but if at all possible, do it. So some tools we use in support, as I mentioned, PMM or Percona monitoring and management. You can check the documentation there. We have pmmdemo.percona.com. Can show you how it works without you having to install anything. We have some test workloads there, and you can check it. Then we use pggather. pggather does SQL queries to PSQL itself, so you don't need to actually install any tools. You just download the SQL script, run it, it will collect the data, and then you can generate an HTML report that you can check. We use it a lot, and it's great. And then pgbadger, of course, you already know this. You can get from the log variables that I was mentioning before, collect more data, and then analyze it with pgbadger. Okay, so these are mainly the 3 tools we use in Percona, and I would like to take 2 minutes to tell you, perfect, thank you, to tell you a bit more about what you can get from PMM in terms of what we have been discussing. So in here, I don't know if you see, is it possible to turn off the lights a bit? So we have the checkpoints activity. Okay, that's fine. If as long as you can make sense of what is here. So this is the checkpoints graph, and as you can see here, we have a lot of peaks, and it's you can see from there, but these are requested checkpoints. Basically, what we are doing, this is forced checkpointing due to max wall size not being enough. So with only this information, we already know that maxwell size is not correctly dimensioned for this workload. Now, at this point, clearly, someone tuned maxwell size, and then we are getting checkpoints every whatever time, but since they are green, they are scheduled checkpoints, which is like the checkpoint timeout being honored by the system and not needing to run faster than that. Then we have the buffers, and this is the shared buffers usage. These are the reads, and these are the writes. So, as you can see here, we were doing an amount of writes, whatever, 2 megabytes, 20, 200, that doesn't apply here much, but someone at this point clearly changed the shared buffers. So it's being doing less and less read I/O until the point where we don't do any reads, and all of the reads are coming from these shared buffers that the Postgres internal cache itself. It's not needing to do any amount of I/O, neither to the OS page cache nor to the disk, right? So this is what we want to see. And then these are writes, and these are writes done by the background writer, which we typically don't want to see because these are due to forced writes before the checkpoint happens. At the end, we can see this spike, and this is you will see here, it says during checkpoints. And this is what we want to see. This is a controlled I/O that we were mentioning before that we can have if we tune things correctly, right? So this is not disruptive. This is not something that you cannot plan for. If you've done everything correctly, you will know that at the 5:30, you will get this kind of workload if you've done things correctly and if your workload is stable enough. And then these are the when a backend connection, so when a client connection needs to do a change in page and the page, the shared buffers is not enough, to bring in a new page, it may need to flash out another page. And if this happens, this backend connection itself will need to do the flash. That is the connection backend doing the flash itself, and it throttles itself to do an amount of work which is set by the BG writer LRU max pages, right? So it does at most 500 pages, and then it stops and it throttles itself. We don't want to do this. This is something we don't want, because that means the connection itself is waiting and it's stuck, and the client will not get the data it needs because it's doing flash, which we should be taking care of, right? But you may be tempted to increase the amount of pages before increasing the shared buffers. So this is a clear example of doing premature optimization that may not give you the results you want, because the issue was on another side. The issue was that the shared buffers was on default and your workload was way higher than it was fit for it. If you increase the shared buffers, this problem will go. But in this case, we tune it prematurely and we increased shared buffer BG writer LRU max pages to 500 when we actually didn't, and it didn't solve the issue at hand, because the backend was still doing flashes, okay? I know that was a lot to process, and maybe I didn't explain it correctly. If you didn't understand, we can discuss it more afterward. But this is the this dashboard. I did it some years ago. PMM didn't have this information from Postgres, and based on the customer tickets that we got and the information that we needed, and our needs in particular for support, I created this dashboard, and this is my pride and my baby. This is the best graph I've ever done, and I don't think I will ever do anything better. So this is how you can size Maxwell size very easily. You don't even need to think about it, right? Because this is going to give you the Maxwell size as you currently have it, and this is aggregated in checkpoint timeout, the amount of bytes that were written to the walls, right? So in here, let's say we have 1 gigabyte written to the walls in checkpoint timeout time, 15 minutes, but the Maxwell size was set to 500 megabytes. So what do we need to do? We need to surely increase it to 1 gig, and maybe if we want to have some overhead, we can increase it even more and be assured that we can even absorb more peaks in our write workloads that we are not getting into now with this data. And if you see, and after I did this graph, it's how I started to learn how the actual checkpointer works. And this was very unexpected for me, because the write workload was the same, but we were doing almost half of the writes to the max wall size, to the walls. So what the hell is going on here? The thing is that by default, Postgres uses full page writes, which is a safe way to do it in case when you have a crash. The first time you write a page, it will write the whole. When you write a tuple, a change, it will write the whole page. So even if you change 4 bytes in that page, it will do the 8K. Okay? And that is how you see exploding, right? Because if you have to do more checkpoints, you will have to start from scratch more often, right? So every time you do a checkpoint, you start from scratch in terms of the pages that are in that wall. But if you increase the checkpoint timeout and you don't do the checkpoints so fast, you will not have to write the full pages so fast, and you will even have less I/O. And this was amazing. And this, if nothing else, this is also a motivation for you to increase the max wall size and to avoid doing checkpoints when you don't want it. And with that, I think I covered everything I wanted to. Again, this is a QR code if you want to check the slides, if you want to download them. If you have any other questions that you didn't want, that you couldn't ask because of time, this is my email, first last name @percona.com. I'm going to be around, and I would be more than happy to discuss things with you guys. I understand Portuguese, I cannot speak it, but I have some translators here, Marce, Bianchi, Charlie. They can help us understand each other. So yeah, unless you have any other questions, thank you very much.